In this video, I'm going to talk about types of distributions, and a distribution is just a collection of data on a certain variable. And what we're going to do is we're going to look at a graph, like this graph you see here, this histogram, and we're going to describe the shape. And there are many types of shapes that have names. We're going to focus on 4 of them in this class. And so this example here, we have the frequency of weights in pounds is graphed. You can imagine there's a group of people and all their weights are recorded, and so this is a graph showing the distribution of those weights. And so you can see from this graph there was a curve drawn on top of the bars, and that's just to illuminate the shape of the histogram. And so we can see that there's this peak here. So the highest class is between 165 and 180 pounds, so that was the most frequent class of weights. And we can also see that on either side of the peak, so surrounding the peak, maybe from around 135 to somewhere between 210, 225-ish, that's where most of the data is. There's very few people that fall on the right-hand side where we have these higher weight classes. I mean, there are people, but there's just not as much of the data as on that right side. This we can call a tail. Whenever the curve goes down really close to the x-axis on one side, we say that that's a tail. And you can imagine that if the x-axis continued to higher weights, that tail would continue to get closer and closer to that x-axis, because there'd be fewer and fewer people that had those that were in those higher weight categories. And so because this tail is on the right hand side, we can say the graph is right skewed. And we say that because most of the data is on the left and in the middle. And so this data on the right is not as common. There's not as many people in those classes. And so those values can skew the rest of the data. So we say it's right skewed. And so we're going to look at 4 different types of distributions. Right skewed is one of them. And the pictures are right here. And so this first one on the upper left, this is also a right skewed distribution. So it's very similar to the one we just looked at with the weights. This one on the upper right, this is what we call a left skewed distribution because the tail is on the left. And one example for real life example where maybe there might be a left skewed distribution might be average lifespan. So you could expect that, that most people are going to be on the higher end of things. And so like the peak here, most people, I would say the average lifespan, at least in the US, is somewhere around 78 or 80, depending on if it's a man or a woman. But you're going to have most of the population be over here on the right-hand side, on either side of 78. And there's going to be fewer people that are going to have a lifespan that is very small, so 10, 15, 20 years. And so that would be an example of a left skewed distribution. And then down here on the bottom left, this is what we call a uniform distribution. And it's uniform because, in this case, if we had, let's say, a bar graph, the bars would take the same value. One classic example of a uniform distribution would be flipping a coin. And so if you were to graph the probability of landing on heads, it would be 1/2 or 50%. And if you were to graph the probability of landing on tails, it would also be 1/2 or 50%. So they're the exact same. So it creates this graph that has a uniform distribution. And then the last one, this is one that looks like a bell. So we call it bell-shaped. Or we call it a normal distribution. And there are many examples of normal distribution. One example would be height. It could be for men or women. They both are normally distributed, and that happens because most people are around average. So for example, the average height for a man is around 5'9", and that's in the middle of the curve. And so most people are going to be on either side of that 5'9". That's going to be most of the population. There will be a few, very short people over here on the left-hand side. There will be some very tall people on the right, but most people are going to be about average, you know, plus or minus a little bit on either side. And so these are 4 examples that we're going to focus on in our class, 4 types of distributions. There are many, like I said, there are many other types of distributions, and you know, in practice there will be variables whose distribution shapes do not exactly fit any of the shapes described as above. And so what I want to do next is talk a little bit more about the normal distribution, because this occurs in real life enough, it's common enough that it's worth spending some time on and looking at the properties of this type of distribution. So here we have another picture of a normal distribution, and let's just talk about some properties of a normal distribution. And so one thing that's really important to notice is that it's symmetric about the mean, and we can even start with the second bullet first. The mean, median, mode are the same, and it's in the very center line. So I put 5 foot 9 inches. I'm just going to use the example of heights for men. And so their average height is 5 foot 9 inches for the US, so it's different depending on the country. And so the mean, median, and mode would all be in the center, and it's symmetric. So it means 50% of the data is on the left, 50% of the data is on the right. It means 50% of men are shorter than 5 foot 9, 50% are, you know, about average or higher than 5, or, you know, taller than 5 foot 9. And so that means 100% of the data total is underneath the curve. And so most of the data, as you can see, is around where the mean is. So, and you can imagine in terms of heights, you know, people you see walking around, most men are, you know, 5'9" plus or minus, you know, a couple inches on either side. And then we have fewer people that are in the extremes. So the extremes, there's 2 extremes. You've got an extreme on the right, and you also have extreme on the left. And so in this example, the left extreme would be very short people. There's not very many of them. And then on the right, it would be very tall people. So you're talking about, you know, maybe a man who's, you know, 6'8" or 7 feet tall. I mean, it happens, but there's not very many. And so that's why you have those tails on either side. And technically those tails keep going. They never touch the x-axis, but they get closer and closer to the point where there's really very little data underneath there. And so almost all the area, so I'm on this bullet right now, is under the normal distribution curve is within 3 standard deviations of the mean. And we'll talk a little bit more about standard deviations in a minute, but I would say, you know, standard deviations might look like this. If we have 1 standard deviation, 2 standard deviations, and then 3, and then 1 standard deviation above, 2 standard deviations above, and 3 standard deviations above. So most of the data is going to fall between, you know, 3 standard deviations, and you're going to have very few on these tails. Okay, and so let's go ahead and do an example where we can make a little bit more sense of the normal distribution, this bell curve, and then those standard deviations I was talking about. So in this example, we have test scores on a math exam that are approximately normally distributed with a mean of 72 and a standard deviation of 8. Draw the associated normal distribution curve and label the axis appropriately. Okay, so I'm going to draw a curve. And I always start by putting a line in the very center. And remember, the very center, this represents the mean, the median, and the mode. And so since the mean test score was 72, I'm going to put 72 in the very center. And then the standard deviation is 8. And so what you can do here is we can draw lines or tick marks, either one, on the x-axis that represent the standard deviations. And so I can mark 1, 2, 3 on the right, and 1, 2, 3 on the left. And so each standard deviation would be, or each tick mark rather, would be 1 standard deviation away. And if the tick marks are on the right, we say these standard deviations are above average. And then on the left, these standard deviations are below average. And so what we can do is we can use the standard deviation of 8 that's given in the problem to calculate what these scores would be at these standard deviation marks. And so all we have to do is add and subtract whatever the standard deviation is. And so to get this first tick mark here, all we have to do is do 72 plus 8. Okay, and so we do that and we get 80. So it means that if a person scored 80 on the test, they were 1 standard deviation above average. And then we can do this again. We can go write one more and we can add 8 to that. And then we get 88. So if a person scored 88 on the test, they scored 2 standard deviations above average. So at that point, you know, they definitely did well, but we're getting farther out from average. So they really did well compared to the person who got the 80. Their score is a little bit more uncommon. And then we can add 8 again if we want 3 standard deviations above the mean. And so 88 plus 8 is 96. And so we get a score of 96 there. So if somebody scored a 96, they are 3 standard deviations above average. That's pretty uncommon. Once you get outside of that, it's very rare. So, you know, somebody who scored even a 98 or 100, this graph shows that, you know, that's really uncommon and they did really well. And then we can go the other direction too. So we can take 72 and we can subtract 8 to go to the left. And so that gives us 64. So if somebody scored a 64, we say they're 1 standard deviation below average. It means they didn't do great, but they're still within the range of normal, I would say, because you can see even if we extend this line up here, 1 standard deviation away from average, you're still, you know, under that bulk of that curve there, that peak of the bell shape. And so it's still considered, you know, I would say more common. And then the 64, we can take that and we can subtract 8 again. Okay, and we get 56. And so somebody who scored a 56 on the test would be 2 standard deviations below. And then we could subtract 8 again and get 48. And so that would be 3 standard deviations below average. And so you can see here, I just labeled all of the standard deviations in case that's helpful. And then just one more note, and I know I already said this, but the standard deviation is going to vary, you know, with every problem. And so in this problem, it happened to be 8, so that's why we added and subtracted 8 each time. You know, in a different problem, it might be something else. It probably will be something else. And so you'll have to always read the problem and pay close attention to what that standard deviation number is.